same. Right, electric circuits, okay? Lots of theory, as I mentioned in this section, okay? But it's still quite a nice section nonetheless, okay? So what we want to just have a look at here in the first slide is looking at EMF, potential difference, and voltmeter, okay? Now, EMF, potential difference, and voltmeter all mean the same thing, okay? Or at least EMF and potential difference, okay? So voltage has two different names. When we talk about the voltage of something, we are talking about the EMF, all right, which stands for, and I know I'm not wrong when I say this, electric motor force, all right? And the EMF is usually used to describe the voltage that's in a cell or a battery, okay? Then we look at potential difference, which is also another name for voltage. So voltage is basically the basic and most common name for itself. Okay, voltage is voltage no matter what it's called. No matter if it's called potential difference, no matter if it's called EMF, voltage will always stay voltage because it'll be measured in volts. Okay, so voltage is almost like the easier form of the word, of the science that we're going to study. Okay, like I mentioned to you in the notes there, which I've so beautifully typed out, if I must say so myself, potential difference or voltage in capital V. Whenever we deal with electric circuits, capital V will always mean voltage. Okay, is supplied by a battery to a circuit where it is connected. Voltage, the definition for it is the quantity of energy that the battery transfers to a unit of charge. Right? Now, charge, remember from electrostatics, is the symbol is Q, and we know that's measured in coulombs, of course. When we're talking about energy, okay, this is the symbol over here, W, okay, that's energy. When we get to metric, W begins to be more defined as work, okay, work done, okay, which is also energy. All right, so the formula for calculating voltage, all right, the most basic and simplest formula for calculating voltage is V for the voltage is calculated by taking the energy transferred divided by the charge, which is V divided by Q. All right, so if I can write it a bit better up here, because obviously I struggle to write fractions in Microsoft, well, not in Microsoft PowerPoint, but in PowerPoint presentations. Okay, V is equal to the energy transferred, all right, divided by Q, which is the charge. Okay, that's the formula for voltage. Okay, V equals voltage, all right, or volts, it was just in volts, right? W, which is energy transferred, which is also the definition for work done. Okay, that's measured in joules, all right? And then we have Q, which is unit of charge, which we know is measured in coulombs. Okay, that's the formula for potential difference, which I'll just write on top, potential difference. Okay, fantastic. Okay, let's go back to our presentation. Now, we measure voltage or potential difference in a circuit, okay, across 2 points, all right, using a voltmeter. Okay, now a voltmeter, all right, is a set of apparatus that you would have seen, all right, had you been in school still and have been doing your practical, because this is a very concentrated section in physics. Okay, love doing pracs on this. Prac is definitely more serious than in most other pracs in physics, of course. With the electric circuits, a nice way to also pick up marks here. And important thing to note about a voltmeter is that a voltmeter is always connected in parallel. Okay, so what I mean by parallel? Okay, obviously we've obviously know what parallel means, all right, from mathematics. Okay, we obviously recognize that. Okay, that if two lines, all right, go across like this. Okay, we see these two little lines on them, we know that they are in parallel. Well, the same thing will apply to something in the electric circuit. Okay, is that a voltmeter cannot be connected, for example, we have something called series and parallel. So we have series, okay, and then we also have parallel. Okay, so your voltmeter will be connected in parallel because if, spelled voltmeter wrong, because if it is connected in series, it will read nothing. Okay, so if I have something over here, if this is my object, my voltmeter will have to be connected in parallel. Okay, can I see that here the voltmeter would have been over here somewhere, that this is parallel to this. Okay, so it's still connected in a parallel way. If it was connected in series, it would have been connected over here on the same line, right? In the same line as the object over here, which would be series. Voltmeter cannot be connected in the series. Okay, it can't. It breaks circuit law. Okay, this is a picture of a circuit. We have a light circuit over here. What I was trying to explain. Don't worry about all these other symbols here. I do have a table that I'm going to represent to you guys on how for each symbol, which you guys can take down as well if you choose to. So here we have what is known as a cell. This is not a battery. Okay, this is a cell. What is a cell? Let me go show you. Can we see over here? We all used to seeing these types of batteries, correct? Yes? No? I have one in my drawer right now.
Yes.
Fantastic. So one of these, just one of these, okay, has a positive and a negative side to it, okay? The one side is positive and the one side is negative. I'm just looking on my battery here to see if it does tell me which side is positive or negative. Yes, it does, okay? Here in the textbook as well, the one side is positive and the one side is negative. So this means I only have one of these bad boys. Only one, okay? A battery is when I have two or more, all right? So this four batteries, in quotation marks, these are actually four cells that make up one battery. Okay, so in your remote control, you'll often have two cells that you need to put in, all right, and that becomes a battery, all right. But the colloquial term, obviously, that is used across the world is that these little ones on this own, they just sold as a pack of batteries, all right. And as a pack of batteries, that is correct, of course, because there's like more than one in them. So that will be a battery. Okay, but just one of them is what is known as a cell. So here we have a cell. Okay, if we had two, it'll be a battery. But we can see that here in this little basic circuit representation here, that the voltmeter is connected in parallel to the circuit. Okay, I will shed light on this little object here. This is called a resistor. Okay, we haven't gotten there yet, but this is a resistor. Okay, it's also been placed in our circuit here. Okay, so not too much to worry about that yet. We'll get there in just a moment. Any questions on voltage or potential difference so far?
Is potential difference EMF the same as voltage, basically? Just different
Yes,
names.
it's three different names, yes, for one of the same things.
Okay.
Cool. Except that when you look at EMF in later on in your physics study, so once you get to like grade 11, you'll find that EMF, which will be written a lot like this, stands for electric motive force, but this will be the voltage of your cell or cells, which will be your battery. Okay, so for example, they'll say that the battery in the circuit or the cell in the circuit has an EMF of 24 volts. Okay, so they're telling you that the voltage of the battery of the cell is 24, but they say it's an EMF. So the EMF will be prescribed to the battery, so they will work hand in hand with each other. You see EMF and cell, EMF and battery, but they're still measured in the same thing. Does that make sense?
Yes, it does. Thanks.
Lovely. All right. We were we. Okay, this is a basic circuit. Okay, in grade 10, to be able to draw a circuit and recognize a circuit and how it looks based on the information that you are given will definitely count in your favor when it comes to answering questions. Grade 11 and 12, you answer circuit calculation questions by just looking at a circuit. Okay, but first you need to, before you can get to that level, you need to learn all the components of a circuit as well, all the components of a circuit before you can answer questions by looking at a circuit. Okay, also we'll take a look at when it comes to resistance. Okay, we definitely will be learning some other enrichment purposes, like why do batteries go flat? Okay, that is a possibility of an exam question at the end of your exam section of circuits. They'll be like, why do batteries go flat? You need to be able to answer that, but I will teach you that in the next coming weeks. Okay, so here we got an example. Right, so I'm going to take you through this example. Keep in mind the formula that or that I showed you here at the beginning, which is V is equal to W over Q, where V equals voltage, W is energy transferred in joules, and Q is in charge in coulombs. Okay, so let's go have a look at this example together. During a thunderstorm, a potential difference of 2 million volts. All right, so we must understand that 2 million volts can be written smaller. Okay, just want to show you guys this before we continue. All right, is that they tell us that the voltage, which we mentioned there, is 2 million volts. Well, that's quite a lot. Okay, but that can be written in scientific notation. Am I correct? Which is 2 times 10 to the 6 volts. Okay, so 2 million, writing out 2 million, obviously we know a million is 6 zeros. It's quite a long number, so we just shorten it by saying 2 times 10 to the power of 6 volt, because 10 to the power of 6, if you just type 10 to the power of 6 in your calculator, if you punch it in your calculator, sorry, not type, but punch it in rather, you'll get 1 million. Okay, so it's obviously 2 times that would be 2 million, and 3 million, etc., etc. You guys all understand that. Okay, going back to the example, bolts up between the cloud and the ground. Eventually, lightning strikes and a charge of 115 coulombs flows between the ground and the cloud. Calculate the quantity of energy that this lightning flash transfers to its surroundings. Okay. Cool. So the other part that they've given us is that the charge that is flows with the lightning strike is 115 coulombs. Okay, so we know, sorry, that's not C, that should be Q. And we all need to calculate the energy transferred, which is W. Okay, so I will give you guys about a minute or a minute and a half to do this question. All right, I'll just, okay, so let's see. I already have my formula that I've already written out already. So let's see. I know that 2 million needs to be substituted for V, but I'm going to write the scientific notation there. I'm going to say, well, it's 2 times 10 to the power 6. Okay, I'm going to just make sure my 10 is around there. Equals, well, W is still my unknown, all right, and divided by a charge of 115, okay? So I'm going to just perform my little mathematicals. Okay, that's going to get rid of 115, and I'm going to have 115 times on this side. So just going to write it on top here. Well, that's not actually going to make sense because it could look like I am re-bracket it. Okay, times 115. Yeah. Okay, so therefore W should equal 2 times 10 to the power of 6, right, multiplied by 115. Okay, and if we do that, then therefore W should be, or the energy transferred, anybody have an answer for me?
I got 230 million.
230 million. All right, so if it's 230 million, should we write it in scientific notation?
So it'll be 230 times 10 to the power of 6.
230 times 10 to the power of 6. That sounds about correct. 230, there we go, times 10 to the power of 6. Alex, finish that answer off for me, please. What is energy measured in?
Oh, coulomb. Oh, for this one it'd be volts.
So volts is measured in, that's potential difference. Coulombs is charge. It starts with the letter of my name.
Joules.
There we go. Joules. All right. 230 times 10 to the power of 6 joules. Okay, that is the quantity of energy that the lightning flash transfers. All right. That was question 1. Let's have a look at question 2. Slightly different. Question 2 says, if 5 coulombs of charge transfers 10 joules of energy each, calculate the potential difference. Okay, so for question 2, okay, they said the charge was 5 coulombs, that 10 joules of energy. Okay, we had to calculate the potential difference or the voltage. Okay, so we write out our formula. Well, V, just scroll a bit down here, is equal to W over Q. It's a straightforward one. We just substitute 10 divided by 5. Therefore, the voltage should equal to, anyone?
2.
2, yes, but 2 what?
2 volts.
2 volts, okay. We got to get into the habit of saying our SI units afterwards, okay, with regards to whatever we are calculating, okay, in physics, of course. So the voltage or potential difference, all right, potential difference also in later grades, you'll see also changes to P dot D, potential difference. So the potential difference or the voltage here is equal to 2 volts. Lovely stuff. Well done, everybody. Right, so what we're going to do now is we're going to move on to current. Okay, now electric current is given the symbol I, capital I. Voltage was given capital V, current couldn't have gotten capital C because people might have confused it with coulombs. All right, not necessarily with charge, but they would have confused it with coulombs, okay, for capital C. So it got capital I, okay. Capital I, electric current, okay, is the rate of flow of charge, okay. Current is basically the flow of charge, okay, because charge obviously flows through current, okay. We can calculate the current or electric current in a circuit or even in a lightning flash if we want to, okay, as taking the current, which is I, is equal to the charge, all right, is equal to the charge or the quantity of charge that passes any section in the circuit, and we take that per unit time. In other words, we divide it by time, all right, which is T or delta T. So, right, is that I want to write that formula out a little bit better. The electric current, capital I, is calculated by taking the quantity of charge that passes any point or section in the circuit divided by delta T, all right, for the time, okay? So we know I, again, is electric current, okay, and then we also have Q, which we know is charge quantity, which is measured in coulombs, and we also know that delta T is the time. All right, time measured in seconds, of course. Charge we know is measured in coulombs. Current is measured in something called amperes, right? French, all right, or shortened for amps. Okay, we measured in amperes, all right, or amps. Okay, and it's denoted by capital A. So whenever we give a quantity of electric current, all right, in our answer, wherever we are stating the answer, we have to say capital A at the end, which says, okay, there is a quantity of electric current here of 11, for example, 11 amps. Okay, we must not neglect the capital A at the end. Now, obviously, we use an ammeter. Okay, if current is measured in amps, then we use an ammeter, all right, to measure current in a circuit. Okay, and from the picture that I have also displayed there for you guys, it shows there that the ammeter is connected in series. Okay, so it's connected along the wire. Okay, not parallel to any object, okay, but it's connected along the wire. Okay, and next question that's probably on everyone's mind is, what type of wire would be used in a circuit? Okay, what type of wire is used in any electric circuit throughout, I don't know, houses, buildings, in places where we find electricity? Obviously, because electricity almost powers our entire lives. You know, we use electricity for power. Okay, and that answer is copper wire. Okay, if you have an extension lead, something's a bit easier that we use every day, a charging cable, you must take a pliers and you must cut it open. You will find some insulated copper wire that is inside the insulated rubber covering, wire covering. You'll find this copper wire, and it will look something like, if I scroll down, textbook, looks something like this. Okay, we can see that over here we got copper wire. That's how copper would look, and obviously it's got the insulated covering so that if you touch it, you know, electricians or us, if we must touch this part, we won't shock if it's on, but we'll definitely will shock if we must touch the copper side, because current flows very good through copper wire. Okay. So, and an ammeter, like I said, is measured in is used to conduct or measure current in a circuit, and it'll look something like, if I can show you, like that. Okay, this is how the object actually looks. Okay, and the voltmeter looks exactly the same, except that it says V instead of A on it. The voltmeter looks exactly the same. It just says V instead of A. It's got these outlets from where if you want to measure the current, you'll stick your wires in there, and then you'd obviously connect your wires to the circuit, and then current would be measured on the ammeter. Okay, this little needle saying how much current is in the circuit or not. All right. Any questions on current so far?
What is the delta T for basically?
Oh,
Again.
the delta T is used to measure the flow of charge or the flow, because it's the flow of charge. So we're trying to calculate the current that's in the circuit. So we take the flow of charge per unit time. Okay, so remember, in a circuit, to measure current, charge is flowing in that circuit because that's what current is. It's the flow of charge. Okay, but in order for us to calculate how much current is in the circuit, we need to see how much charge passes through that section of the wire um, per unit time. So if we're taking 5 seconds, if we're taking 10-second intervals, we need to know how much charge passed through that entire circuit or past that section in the circuit in 10 seconds. If we get an answer like 115, then we'll take 115 divided by 10 and we'll find out that the current in the circuit is 11.5 amps.
Oh, okay, thanks.
You're welcome. In fact, that's what you guys are going to do now for me. If we go to our next slide, boom, we have some examples. Okay, now here we can see that the thunderstorm example is used again. Okay, so let's have a look at question 1 quickly. Question 1, during a thunderstorm, a lightning flash that lasts for 0.9 seconds transfers 30 coulombs of charge between the cloud and the ground. Calculate the current that this lightning flash represents. Okay, so again, we always start the question by writing down our formula. I is equal to Q divided by delta T. All right. Q we know is 30. All right. Time we know was 0.9 seconds. It's everything that we need on this side of the equation is in the correct SI units. Charge is in coulombs. Time is in seconds, of course. So we can go ahead and perform this calculation, and therefore, all right, Alex mentioned that she has an answer. So Alex, can you go ahead and give it to me?
33.33, but it was recurring, so
Okay,
would we
that's
just
good. You just rounded off to 0.33. All right, because it's going to recur all the way through. Amperes or amps, so it's just capital A. There we go. Excellent. All right. Did everyone else get that? Yes, no, maybe? All right, just let me know in the chat. All right, let's move on. While you guys are letting me know, I'm going to just scroll down here and just prepare the landscape. I'm not going to do any housekeeping for the second question, which is now, if the current in the circuit is 1,3 amps, so they've given us I, calculate how many electrons pass through any point of the circuit in 1 second. Okay, now this is quite a tricky one, or can be a tricky one if you don't read your question properly. So for number 2, right, the most important thing that we need to do here first is find out what is the quantity of charge that passes through a point in 1 second. Okay, so we first need to know Q. Okay, so we have a formula, I is equal to Q over delta T. All right, if we must find out Q and rearrange the formula, Q will equal to the current multiplied by delta T. In this case, we have 1.3 amps, all right, multiplied by 1, okay, because it was in 1 second, and we get the charge or the quantity of charge to be 1,3 coulombs, right, for number 2. All right. So now the next question is, how many electrons is one charge made up of? Well, if we have this formula, Q is equal to N, all right, times QE. How many electrons does one charge have? So if the charge on there is 1 equals to the number of electrons, well, minus times 10 to the negative 1,6, sorry, times 10 to the negative 19, right? If you divide 1 by a negative 1,6 times 10 to the negative 19, you get the number of electrons that 1 coulomb has, okay, to be made up of about negative, because the charge on electron is minus, okay, it is minus, uh, to be 6,25 times 10 to the power of 18 electrons. All right, so the number of electrons that 1 coulomb of charge has is actually, if we take out the negative sign for just a moment, all right, we'll have, well, it's 6,25 times 10 to the power of 18 electrons. Okay, that's the correct answer there for the number of electrons that one charge is made up of. We have not 1, but we have 1.3. Okay, so how do we do this to calculate the number of electrons per 1.3 quantity of charge? Is we take, well, N for number of electrons, we're still going to use that. And we're going to take 1,3 multiplied by 6,25 times 10 to the power of 18 electrons. Okay, like I said, that negative there is just to show that it is for electrons negative. Okay, I could have omitted it. I didn't have to put it in. If I do that, I'll get an answer of the number of electrons that is, if I just go back to the question there just to describe what they were asking, question 1.3, sorry, 1.2 said, how many electrons pass through any point of the circuit in 1 second? If we perform this calculation, we get an answer of 8,13 or 8,13 times 10 to the power of 18 electrons.